In this video, we're going to learn how to conduct the Kruskal Wallis H test step by step. Kruskal Wallis H test is the non-parametric alternative to one-way ANOVA test. So what we are going to do here is using the example on page 119 from the textbook to learn how to calculate the H statistic and compare that with a critical value, come to the conclusion. So in this data set of 17 participants, we are trying to use the data to answer a research question whether people's self-confidence is influenced by their level of social interactions. So I have an ID number for each of the participants, and the interaction level are marked as 1, which is high, 2, which is medium, 3 is for low social interaction. So the self-confidence has a score range from 1 to 25. So what we have here is the scenario from the textbook, but I want you to be reminded that I actually changed some of the scores. So later on, I have a more complete way to demonstrate how to get the correction for tight score. So here we have 17 participants in 3 separate groups. They are independent of each other. And we start with a null hypothesis that the median level of self-confidence are not significantly different for participants in the 3 levels of social interaction. With alpha equals 0.05, we are going to calculate the H statistic and compare that with the critical value. That will lead us to the conclusion. This is the formula for calculate the H statistic. The N, the big N, is the total sample size. We already know that we have 17 participants, so N equals 17. The K here is number of groups we have, and we have the high, medium, and low social participant, so that is K equals 3. To find out the values for Ri's, we need to start with sorting all the 17 scores. We'll put all the 17 scores together, sort them from low to high, then we're going to give them ranks. So the ranking is based on all scores together. So 1, 2, 3, and I have 3 tight scores after that. That should have taken the place of 4, 5, and 6. So each of them will take 5, 5, and 5. And next one would be 7, 8. I have 2 12s. Those are tied. So they would be in the rank of 9 and 10. So I would have 9.5 and 9.5 for each. After that, I have 11, 12. Now, for the 2 19s, they will have the rank of 13 and 14. So now they have 13.5, 13.5, and that gave us to the next rank is 15, 16, and 17. Okay. As soon as we're done the ranking, we can actually go back to their original groups. To get the Ri's, we just simply add up the ranks within each group. For example, Ri, when I equals to 1, so that's for the first group, Ri would equal to the total of all the 6 ranks in this group. I have RH here because that's how the textbook labeled this group. But you know that I can label the group as high, medium, low, or 1, 2, 3. Okay, so this is our I equal when I equals 1. So when I equal to 2, we have R2 equals the sum of the 5 ranks in group 2 and R3, which I equal to 3, we have the sum of ranks in the last group. And N1, N2, N3 are the group sizes of the 3 groups we have here respectively. So we know N1 equals 6, N2 equals 5, and N3 equals 6. We are ready to do the H statistic. But I think it's a little bit easier if we can do this part first. So which means I want to do the R squared divided by N for each group first before I do the entire formula. So for group 1, we have R1 times itself divided by the group size. Alright, we're going to do the same thing for group 2 and 3. I'm going to just Control C to copy and Control V to paste. Alright. Now, let's do the H statistic. H equals 12, which is a constant in the formula, divided by, in the denominator, the overall sample size times itself plus 1. Then we're going to times the R squared divided by N for the first group plus R squared divided by N for the second group and plus R squared divided by N for the third group. Then we finish this calculation by doing the subtraction. 3 times the sample size plus 1. Okay, here we have a obtained H statistic 9.71. If we didn't have tight scores, this is the H obtained statistic we end up with. But in our case, we actually had tight scores. If you remember before we rank the scores, you see we have one set of ties with 3 values and 2 sets of ties with 2 values in there. So we actually need to calculate a correction for the ties before we declare, okay, this is our final H statistic. So I'm going to show you how to calculate the correction factor by using this formula. So C for the correction for the H statistic equals, we start with 1 minus, in the numerator, we first know that we have one set of scores with 3 values. So t equals 3 in that case. To the power of 3, so we simply just, times itself times itself. Okay, then minus 3. Then we remember we have two sets of ties. Each set have 2 values in there. So t equal to 2. In that case, we do t again to the power of 3 minus t again. Okay, this is the 3 sets of ties in the numerator. Divide by the denominator, which is 17, remember, to the power 3, so times itself, then times itself again, minus 17. Okay, so the correction is very minor, is 0.99. Now remember, sort the data set back to the original order, and here it's your final H statistic that equals to this value divided by the correction factor. We have a H value that's 9.78. If you use these three group sizes like 656 and alpha equals 0.05 to look up the H critical in table B.6, you will find the critical value 5.76 on page 249. So compare your obtained value 9.78 with the critical value. Since it's greater than the critical value, you're going to reject the null hypothesis, and the conclusion is that the median level of self-confidence are significantly different for participants who had different levels of social interaction. And to find out exactly which group different from which group, you need to do the post hoc test. In our case of independent sample test, we can use the Mann-Whitney U test for that purpose.